So in the last video, I talked about the idea behind Taylor series and what it actually tries to do. It sets the stage for higher level math and science, because when we get into higher level math and science, especially with differential equations, we sometimes can't find solutions to differential equations or an explicit solution to it. And the way we end up trying to solve that is by approximating functions to be polynomials, because polynomials are actually much easier to work with than stuff like sine of x and cosine of x and natural logs and any weird function like that. So Taylor series just helps us solve that problem, and it also starts to approximate more functions that are called transcendental functions and model a polynomial that closely relates to the transcendental function, such as sine and e to the x. So we're going to be talking about, in this video, more of the math behind it, because in the last video we just looked at a bunch of ideas and kind of visualizing what Taylor series tries to do, but now we have to look at the math that describes Taylor and Maclaurin series. And I have the word Maclaurin here, and Maclaurin is just a special case for a Taylor series. And we'll see exactly what I mean by that. So what is the formula for Taylor series? There is actually one formula that applies to every single thing, which is very interesting, that it's not just sine of x being its special thing and e to the x being its special thing. It's actually generalized to every single function, which is very interesting, that any function can be written in this form. It's the infinite series from n equals 0 to infinity of the, I guess the entry is the nth derivative, so that parentheses on the exponent means the derivative of, evaluated at this point a, divided by n factorial, times x minus a to the nth power. And that's a lot to handle in just one simple equation, but it actually describes so much. It describes sine, it can describe any polynomial, it can describe e to the x, any form of any function. It can be like sine of cosine of sine of x, tangent of e to the x. It applies to every single function and any composition of those functions. So this is Taylor series. I would highly suggest memorizing this. And if you memorize this, you don't really have to memorize everything else, because if you know this, it will help you, I guess, go through the process of getting to the other equations that people like to memorize as well. So in case you forget the formulas people like to memorize, as long as you remember this, you'll remember, or you'll be able to get to anything else that relates to Taylor series. So this is a Taylor series. How do we get from Taylor to Maclaurin? Maclaurin series is just a special case in that we let a equal 0. So it's still the same, the infinite series as it goes to this, of the nth derivative evaluated at 0 this time, divided by n factorial, times, since a is 0, it's now just x to the n. So this is the Maclaurin series, or the form of Maclaurin series. Basically, a equals 0, and this is at any a. So now let's talk about the formulas. Why is it like this? So let me just scroll down here. Why is it like this? Why is it written as n factorial? Why are we raising it to a power? Remember that in the previous video I said that Taylor series matches any type of function looking at its derivative at that point. So here we have the derivative at that point. So if we match the first derivatives at the point 0 or at the point a, we can start to model the function. And then additionally, we have to have this x term here because we are taking derivatives of stuff, and then we can just use the power rule. So we're going to use the power rule, matching it through power rule stuff to model the equation. But then we have n factorial. What's that purpose? If you remember from taking the power rule, it's going to be something like this. So I'm going to take the first couple derivatives of x to the n. So x to the n would be this, and then x n minus 1, x n minus 2, and then let's do one more. Notice that if we continue doing this, this coefficient here starts to look like n factorial. So the way I think of the bottom is that it kind of balances out that thing when we keep doing the power rule over and over and over and over again. This thing, when we take the power rule, will be balanced by dividing by n factorial. That's the way I think about it. So, in all, I guess the key takeaway here is that the Taylor and Maclaurin series matches the behavior of a function by looking at its derivatives, by increasing the derivatives, right? So now we want to find the 0th derivative or its plain simple thing, and then we try to match its first derivative, and then we match its second derivative and its third derivative and its fourth derivative all the way to its infinitieth derivative, which would take a long time. But if we are successful in doing that, we basically can write any function as this. So let's start looking at one. I want to look at the one we've been looking at the entire time, sine of x, and start looking at it. So let me write the Maclaurin series. So the way we do that, let me just write the formula here as a reminder. This is the one you have to memorize. But it's a good formula to memorize because it's really interesting in what it tries to do. That is the Maclaurin series in its, I guess, most generalized form. Okay, so what is it? The function we're looking at is sine of x. So that's what that f of something is. But now we want to start taking the derivatives. The first derivative is equal to cosine, and the second derivative is equal to negative sine, and then its third derivative is equal to negative cosine. So let me just stop there. We can go on forever if we really wanted to, but then we have the second part. We want to evaluate it at 0. So if we were to evaluate it at 0, f of 0 is equal to, well, sine of 0 is 0. The first derivative evaluated at 0 is 1. The second derivative evaluated at 0 is, well, it's 0. And then the third derivative here is negative 1. Okay, so now we know that. It kind of seems like we did something. We talked about the numerator, and now we just fill it into this, because these things will always be the same. It will always be x to the n and n factorial, but this top depends on what the function is. So let me write it in red because this is where we're trying to get at. Let me write the first couple terms here of this Maclaurin series. So if I were to write the first, let's say I did up to n equals 3. Oops, I accidentally scrolled up. Let's go all the way to n equals 3. So let me write 3 here. So we're only going to 3. So it's the 0th derivative evaluated as 0 divided by 0 factorial times n to the 0th power plus the first derivative evaluated at 0 divided by 1 factorial times x to the first. And then I guess I have to scroll down here because I'm going to run out of space, plus the second derivative evaluated at 0 divided by 2 factorial plus the third derivative evaluated at 0 divided by 3 factorial times x to the third, and then I forgot x squared right here. So now we just start filling it in. I know this. This is 0. 0. The first derivative evaluated at 0 is 1, so this goes to 1. The second derivative here goes to 0. And the third derivative goes to negative 1. So we see this whole this cancels out and this cancels out. So what do we get? We get only these two terms, which I found to be 1 and negative 1 as the part that this numerator evaluates to. So now we can just simply write it as, let me write it in blue. So it's equal to 1 divided by 1 factorial times x, and then plus negative 1 divided by 3 factorial x cubed, and then let me just write it more nicely. 1 divided by 1 factorial is just 1. And then let me bring this over here, so it's going to be minus x cubed divided by this. And this was actually the first two terms of the series. And then if I ask you to do it with the first, or going to n equals 5, we're going to do that same process, and we're going to end up going to this. And then if I say n to the 7th, we're going to go like this. But that just involves taking the derivatives of this function and start to evaluate it at a point 0. If we were to continue this on and on forever, we get the Maclaurin series for sine of x. So what is that? X minus x cubed divided by 3. So let me write it like this: plus minus, and then plus x to the 5th, this, and then plus minus 7, or x to the 7th divided by 7 factorial. So what would happen if we were to continue this forever? Or in other words, what is its nth term? What is its nth term? So the first note I want to make is that, let's say this is 0. Let's say this is term 0 and this is term 1, 2, 3. So this is n equals. This is just important for when we write the series for it. So let's think about this. It alternates signs, so we need an alternating sign thing, and the way we do that is by, let me scroll down here. Right about here. Perfect. So n equals 1, n equals 2, n equals 3, all those. Let me write it back in red. So we have an alternating sign. So the way we do that is by -1 to the n. And we need the first term to be positive, so if we plug in 0 here, it's going to be a positive number. Okay, now what? We are looking at odd stuff, right? All the exponents are odd, all the factorials are odd. Let me write it like this just to make it clear. So how do you represent something odd? Well, the way we do it is by kind of like looking at a pattern. If 2n is always an even number for any n, 2n plus 1 must be odd because it's always going to be an odd part to it. So let's do that. We have x to the 2n plus 1, and always double check to make sure that first term is true. If we plug in n equals 0, it's going to be x to the first power, and that's true. If we plug in n equals 1, it's going to be x to the third power, which is true, and then we continue this on, just to double check ourselves. And then we want to divide by odd factorial, so we kind of want to do that same pattern here. Factorial. So we have that same pattern here. We can always double check. If we plug in n equals 0, we're going to get 1 factorial. If we plug in n equals 1, it's going to be 3 factorial. So this is the nth term. We just found the nth term. And now we kind of want to go back to the infinite series and start putting this in. And we found this. This is equal to sine of x because we're going to infinity terms. This is exactly equal to sine of x, and what we just found here is an important fact. It's the Maclaurin series for sine of x at x equals 0. And I guess a quick way to go from n equals 0 to n equals 1 is actually using the Taylor series expansion, and we would just do the same thing here. It would be, let me zoom out here. There we go. We would have to use this formula here at any value here, and that might take a while because Taylor series is going to get harder to use than Maclaurin series, because instead of plugging in 0, we have to plug in whatever value. Usually it's going to be something nice like pi or pi over 2, for example. But then for other functions, it could be like 1 or like 5 or -1. And we just simply plug it into the formula above here. And then we can get a Taylor series. We probably want to find the nth derivative, or not the nth derivative, the nth term, and then write a general infinite series that perfectly matches the behavior. And this perfectly matches the behavior of sine. I guess if you wanted to double check me, write out the first couple terms, maybe like the first 7, and start finding the derivatives of those terms, and find the derivatives of sine and see how they match at x equals 0. And you'll see that the derivatives match at x equals 0 exactly. So that's it for this video. Hopefully you got more of an appreciation of how Taylor series works and how Maclaurin series works. Seeing how this formula works and all the parts to it, how n factorial kind of balances out repeated uses of the power rule, and how we have to evaluate the nth derivative at points to match the behavior at that point. So that's all for this video. In the next video, we're going to be looking more into Taylor series and Maclaurin series.